Okay, 201 with yeah, I'm sorry, I'm about 30 seconds late, I think. It was the little issue we had with some audio earlier. I forgot the other little thing I have to do before I do these things to make sure I can sit here for 2 hours. Uh, Things like that happen when you reach the age of 80 or so. I see we have 6 folks out there. That means, as my, did I turn on my, yeah, I have my audio on, I guess. Um, let's see, we have Brian, John, Carl, Peter, William. Uh, let's make sure everybody can hear everybody. We've had a little bit of problem, and feel free either to do a raise hand. What we try to do here is save the chat box for communicating with the, oh, wait a minute, maybe that's all we have now. Wait, I'm sorry, I didn't get checked. Yeah, there's also Q&A. If we can do questions and answers and Q&A and save that for the interaction coursework, and then if there's any interaction to be done with the host, do that on the chat box. Now, if let's have that kind of as a general rule. But if one doesn't work, then certainly there's always a plan B out there, hopefully. So what I need to know is, I'm looking at my participant box right now, and I'd like to see if it shows if hands are raised. So if you can hear me, would you please raise your hand? Peter, you must be able to hear me. John, William, Brian, Carl, and William again. Okay, great. So we're good to go. All right. Well, welcome to this wonderful, almost sunny, I don't know what you kind of weather you have up here where you are. We're getting some interesting, threatening lightning, thunder. Who knows what's going to happen to the power here this afternoon? But that's, I guess, what we're here to talk about is electrical trends. So let's get on with it and talk about electrical trends. Times are changing. Really? No kidding. Don't have too many of these anymore. Although the one on the lower left is kind of the one I learned how to type on a long time ago. But that's actually my calculator and my slide rule there. And that's a light that we used to have in our cabin up north until we finally got electricity in about the mid 1950s. So yeah, things are changing. And for the most part, changing for the good, hopefully. Certainly how we generate and use electricity, that's changing a lot. And there's still some of this out there. There's a fair amount of this out here. Just drive certain places. I believe this, I don't remember where I took this picture. Maybe I didn't even take it, but I think I probably did. It looks like maybe it's northern Massachusetts. And then there's stuff like this out there. The solar stuff, they call it, I guess. Don't let me fool you. That's what I do right now as a 82-year-old retired electrical engineering professor. I do final checks on photovoltaic systems. And in the past 2 days, I've looked over 82 kilowatts of residential PV systems, average about 13 kW a piece. So there's some folks still deciding that they want some of this stuff, and I doubt that it's a political reason. My guess is they see that their neighbors have it and it's working well, and they look out and they see that there might be a hurricane coming, and they look at their electric bill and they see that from their neighbors that they might be able to cut that down a little bit at a reasonable cost. So people are still installing photovoltaics, and so things are changing. Lots of windmills in Iowa and the Midwest and California and other places where there's lots of wind. Not too many off the coast of Maryland right now, but they're trying. Um, and well, there's a fair amount down in Oklahoma. And talked to a friend down in Costa Rica. They're installing windmills down there like there's no tomorrow. So, and other places. So yeah, things are changing. We thought we'd maybe chat about that a little bit today about what the driving forces are. And let's just see what we can come up with. What is happening anyway here? Well, for one thing, second law of thermodynamics stuff, the heat engine type thing where you burn something to make electricity, that's kind of inefficient. There are certain other ways that are more efficient than that. We're switching from non-renewable to renewable. That is, I would have to argue the sun will be gone in 4.5 billion years. So, and then we'll have 8 minutes to figure out something else to do. Maybe they'll figure it out before that. But 4.5 billion years is a reasonable window for me. And so, there's nobody's figured out how to charge for the sun yet either. How many kilowatt hours, how many cents per kilowatt hour for every BTU or kilowatt hour of sunlight that impinges on the planet? I'm not sure. Uh, some of the sources are ever so slightly dirty. In other sources, certain things are pretty clean. On the other hand, the fossil sources and the nuclear have generally been pretty predictable, and the wind and the solar. Well, solar, kind of predictable that nobody expects it to shine at night. But otherwise, nobody's going to argue that it's less predictable. Although it's amazingly predictable on a longer term. It's just from minute to minute basis. It's kind of hard to know what's going to happen. But in a month's time, it's got a lot of software out there to predict exactly, well, not exactly, but pretty closely to how much you're going to collect. There's been some storage around, but not a whole lot of energy storage. But now energy storage is going through the roof. Well, not through the roof or on the roof, but it's just lots of it happening. More high voltage DC transmission lines are being built. And there's a whole lot more control and data analysis going on. So one of the reasons here is because the cost of photovoltaics, for example, has been going down like crazy. Between 1976 and 2024, its cost per watt has dropped by about a factor of 500. And it would have dropped by a little bit more than that had it not been for tariffs, because it's interesting. You notice on here, we're looking at something like 20 cents a watt. But I'm told that if you go into other countries that don't have tariffs on photovoltaic modules, that wholesale large quantities, you can buy them for about 10 cents a watt. So that would be a factor of 1,000, which is pretty substantial. Pretty substantial. Not too many other things have come down by that, although some of the fancier electronic things, and of course that's the reason, because they're basically electronic things. So because the price has gone down, the shipments have gone up. And you notice that that's an exponential scale on the left-hand side. So this sort of jagged, crooked line here, if we were to draw a straight line and look at a trend, the trend has been exponential with a pretty high annual doubling, year-to-year doubling rate. So they're being manufactured in a lot of different places now, not just the Chinese. There are quite a few now being manufactured in the United States. And of course, down Southeast Asia and Japan and other places. In 2024, residential installation was about $3 a watt. And 2024, for if you're a utility, the installation cost was about $1 a watt. And we'll give it plus or minus 20% change in that $3 a watt figure, because if you're in Miami, Florida, designing at 175-mile-an-hour wind, you got to use a little bit more material to keep that thing from blowing away. Whereas if you're in Illinois or Massachusetts, the cost is maybe not quite the same because you don't have the same issues with wind loads. And of course, if you have an issue with other kinds of loads, earthquakes or whatever, that can add to the cost. In any case, that's one way of measuring the cost. Another way of measuring, well, what about countries? What are other people doing? We're talking about the United States. This is what happened in 2023. This is the additional amount of photovoltaics that were added by these countries in 2023. And notice that China at 236 gigawatts in 1 year. European Union, 55.8. Of course, European Union has a number of the other countries here. I got to move my closed caption box out of the way so I can read my slide. Okay, Germany, Spain, Poland, Italy, Netherlands, part of the European Union. So that collective 55.8% is from these other countries. But look at where the United States is, 33.2%. Compared to China at or not 33.2%, 33.2 gigawatts versus 236. That in 1 year. So whatever we're doing here, we're not the only game in town. There's plenty of other folks, in India, in particular, is coming up really fast. They're not wasting any time at all. So it's interesting to get a picture of what's going on around the rest of the planet, because we have to realize that we're not the only guys out there calling the shots. Main Germany, okay, there's a note about the European Union. Okay, how about wind power? What's going on there? Well, 2023, we had 125,580 people employed in this industry in the United States. Worldwide, 2023, 117 gigawatts of wind installed, 1,047 gigawatts worldwide cumulative total in 2023, 946 onshore, 75 offshore. Lots of small wind turbines are out there, but it's a little hard to find the capacity, because I don't know, try Googling that after it's over. The number I've been seeing is somewhere in about maybe 100 gigawatt range, and maybe less. But it's there. You see the smaller wind turbines once in a while as well. If you're up in northern Massachusetts along Highway 2, you probably see a few. If you're driving down Interstate 35 down across the middle of the country, you probably see a bunch of them in Iowa, western Minnesota, and so forth. Wherever the wind is, you'll see the windmills. You see windmills up in Newfoundland and other places as well. Lots of them down in Costa Rica, onshore, offshore, both. Construction costs on wind, about $1.30 a watt. And let's face it, people would not be building these things and installing these things unless they could sell the product and make a profit on it. So the driving force here is not something about, oh, let's save the planet and all that stuff. It's because this is now one of the least expensive methods of generating electricity. And there are some of those folks who actually want to try to save the planet, and more power to them as well. The only thing about wind is you need sustained winds, and you can't find those everywhere, but there are a lot of places where you have reasonably reasonable sustained winds. And the folks who install the windmills, they know where the wind is. And if there's wind somewhere, they are probably working on permitting to get some windmills installed. Very good report on wind if you want to read this one. By the way, the presentation, we've got in a PDF format, and our hosts will be happy to provide it to you if you find any of this information interesting, or if you want it, you're free to use it whatever way you wish. I'm giving you that personal permission right now in terms of being the one who has copyright on it, or permission rights or whatever. And we have pretty well documented every place we got our material. Okay. So here's your picture of the worldwide growth in wind power, and this is somewhat less exponential, but it almost looks more linear, and that's why it's on a linear scale. But from 2014, it's gone up from somewhere in the neighborhood of 375 gigawatts up to I went a little too fast there. And where is it? Again, what a surprise. China. Now, United States here, I want to notice now again, though, we're talking about a log scale on the vertical scale here. So that China is still, we're looking at 150 or so for the United States versus almost 500 for China in terms of cumulative wind power. In fact, here's some numbers so we don't have to try to guess at what the values are. So the only difference on wind and solar, solar kind of helps the wind to blow by heating and causing various pressure differences. But you can't necessarily install wind wherever you want to put a windmill and get cost-effective power from it. But for the most part, photovoltaics, since the production is linearly proportional to the sunlight intensity, it's pretty much cost-effective almost wherever you install it, whether it's in any state of the United States, Canada, Alaska, or any other country in the world. So anyway, the trend drivers, call it whatever. Anyway, there's where the action is. If we look more generally here, excuse me, I'm going to mute while I cough, and then I'm going to be right back. Yeah, I'm sorry, I swallowed something a little backwards at lunch. Didn't go down quite the right tube. So let's take a look at worldwide consumption by primary energy source, okay? It looks something like this. And of course, the big ticket item here is crude oil. And that's where more energy, this is primary energy. Now, for every BTU or every kilowatt hour or whatever measure you want to use on this primary energy for the petroleum, for example, with crude oil, you maybe only get 3 or 3.5 or 0.3 or 0.35, 35% or so, because most of that's burned. So keep in mind, this is primary energy. And the amount that goes in. So we have here crude oil, coal, natural gas, and of course there's it on the top. That's what we've been using mostly lately. And you see hydro there. It's going up a bit. You see nuclear, it's staying kind of level. It's not really sure where it's going to go. But they have to get the cost down in order for it to go further, because all of the other sources are more cost effective right now than the nuclear. The interesting thing is the question mark. What's going to happen in 2028? And that's only 3 years away. But it is highly likely that worldwide, the generation by renewables, not including hydro, if we include hydro in with the renewables, then we're looking at hitting the 100 quad level of energy from renewables. Right now, the electrical energy generated in the United States is roughly 24% as of 2024. It's almost 24% renewables, including hydro. So it's going that way. So talking about trends, that's the name of the title, and this is kind of what's happening. If you want some more specific, these are the actual quad numbers. It's a little hard to read the graph here. So these are the numbers that are on the plot. And we're looking 2023, a total of 588 quads. And you can now do the percentages of renewables, 48 out of 588, and get some idea of how that fits. Now, when we say 24% of electricity was generated by renewables, but then we got the uses of the other fossil sources, like in automobiles and transportation. So that's why this 25% of all energy use is not renewables yet, only for generation of electricity. Okay, so what about that? And where are we going here? No carbon dioxide. The sources, that's 18.7% of all of the energy here is 18.7%. And what's interesting is that folks who first started collecting this data were the British Petroleum people way back, and others have now picked up with them and extended and continued collecting this data. So, what's happening in grid use? What's going on? It might affect what's going to be the planning and everything. Well, for one thing, electric vehicles. There's a couple of kinds: all electric, plug-in hybrids. Two of the jobs I worked on just the day before the webinar involved installing electric vehicle chargers in the places where they had the solar. So people are buying electric vehicles. Why? Because they like them. I don't know how many of you have electric vehicles. Let's just, for the fun of it, let me turn on my uh, my Q&A thing. So if anybody have an EV out there? Oh, wait, I don't want to. Let's see. What I really want to do is the participant box. That's what's going to tell me you can just raise your hand if you have an electric vehicle. It's a curiosity thing. Okay. Yeah, well, we're not up to 10% anyway, so we wouldn't necessarily expect that anybody in the group have. I have a plug-in hybrid. We've had it since 2018, and about the only other thing I might want would be an all-electric, but we don't drive very much, so with a 50-mile electric range, we mostly go all electric on it anyway. Pretty nice car, and everybody I know who even owns a whatever electric car, whoever made it, generally the owners like them. So, and one way or another, there's projections by the Edison Electric Institute that there will be a whole lot of them on the road, so that's going to affect the utilities and their need to generate electricity. Energy efficiency is making a difference in what happens with the grid. Energy efficiency was particularly important back in the 1979, late 1970s, when during the oil crisis, while utilities were switching away from oil, And that bought them some time to switch over to natural gas from petroleum or any other sources they might be able to get their hands on. But there's a lot of energy efficiency going on. We'll talk about some of the various things. And there's always the zero energy building thing. That doesn't mean they're energy buildings that are not using any energy. It's just that they produce as much as they use. So, but not necessarily all at the same time. So that means they sell back an amount equal to the amount that they purchase. And distributed generation and energy storage are a big thing. I mean, when you get there's a lot of rooftop solar out there, that's kind of all over the place. And the energy storage is a big deal because certainly, what are you going to do at night unless you save some of the electricity you make during the day? Or what are you going to do when the wind stops blowing unless you save some of it? So you have to figure out. So energy storage is really big time now, and costs are coming down and improvements are being made. And strangely enough, whenever we find something that people seem to like, people seem to work on it and try to make it better. And one other thing is data centers. We're going to talk a little bit about data centers, and data centers are pretty amazing stuff. We'll see a little later. Let's spend a couple minutes on electric vehicles. And there's a lot of different kinds. This is a plug-in hybrid, the one that last came in on the lower left. And excuse me. I kind of like that little BMW. But then again, if you really want one, you get that hot, you get a hot Mustang or something. But look, quite a lot of choices out there on electric vehicles. Let's see. They have to be charged. And of course, engineers will be involved in designing charging stations. So if you're going to do that, what's involved? Well, first of all, National Electric Code has a chapter on it, 625. And one thing it does is recognizes what's an electric vehicle. And what's interesting is when you get to the bicycles and the scooters and the skateboards, whoops, I didn't spell skateboards correctly. And the one-wheelers, and well, if you want to call those who knows what, interesting, if nothing else. But in any case, golf carts, forklifts, and so forth are not part of it. And one thing that's required about an EV is they have to use rechargeable batteries. So if you try to use these batteries in an EV, they wouldn't work because they are not rechargeable. Although I have to say that the batteries in my hearing aids right now are rechargeable. So maybe I could use those hearing aid batteries as maybe I could be classified as an electric vehicle or something since I'm using rechargeable batteries, at least when I'm wearing my hearing aids. Let's look at fuel costs per 1,000 miles. Again, this explains why some people are buying electric vehicles. And again, these are assumptions. You got to assume something. Let's say $4 gas. Okay, it's $3 now, so fine. Change everything by 75% or knock off 20. It's taking only 3/4 of the number, but then again, 15-cent kilowatt hour, that's a little more expensive, except if you're buying on a bulk rate, then that's a little different. So in any case, we'll use these numbers as rough numbers. If we look at 1,000 miles, 50 gallons at 20 miles a gallon, $200 worth of gas. Small SUV at 30 miles a gallon, $133.20. If we use a hybrid sedan, then we're looking at $72.80 if it gets 55 miles to the gallon. An electric vehicle or plug-in, if they're operating all electric, and get about 4 miles per kilowatt hour, which is what a lot of them advertise. And that's when they're not running the air conditioning and a few other electrical things inside, but 3.5 is still not a bad number to use. We're looking at something like $37.50, $40 or so for that 1,000 miles. And which is, you see, about half the price of the hybrid. And you go 50-50 on a plug-in hybrid, and you're still doing pretty well. But like I say, on our plug-in hybrid, we're getting more than 1,500 miles per gallon of gas because we don't drive very much. Getting old, and it's pretty competitive out there in the highway, so we try to let other people do the driving. Now, what are the charging levels? There's 3 different levels. Level 1 is a 120 volt thing, and the typically maximum of, depending on whether you're on a 15 amp or a 20 amp circuit, either 1,440 watts or 1,960 watts if you're on a 20 amp circuit. Level 2, 208 or 240 volt, and most of the chargers I've seen are single phase, and for level 2. And so a 7,600 watt uses 31.7 amps. So that needs a 40 amp circuit breaker. 9,600 watts charging, that's the 50 amp circuit breaker because you have to size it at 125% because it's continued to be considered as a continuous use circuit. And if you got 16,640 watts at 208 volts, that's an 80 amp. And that's going to take it to a 100 amp circuit breaker. So that's all level 2. Level 3 is DC charging, and that charges in generally at 125,000 watts and up. So the DC voltage is sometimes as high as 1,000 volts. It could be, and we're talking, if you talk about buses and trucks and other larger vehicles, that's pretty high charging rate. So in any case, if you're running at 208 volts 3-phase, that's 347 amps. So we're not talking about residential options here for level 3 charging. That's what you find out on the highway. So, these are small compared to some of the stuff that's coming up. So these are things the utilities are going to have to be paying attention to, and we're going to take a look at what it might take to take care of the charging and needs. Here's your level 3 chargers, and the whole idea here is that go in for your hamburger, half hour later you come out, you picked up about 200 miles of driving, and after 200 miles you go in for another hamburger, another fill, and pretty soon your car's full of electricity, and your car stays full of wait a minute, no, your stomach is full of hamburgers and your car is full of electricity. That's the new way that we charge cars. Unless you charge them at home, then you can eat other things. This is the charger connection for the DC, the big time level 3 charger. You can see those big leads there for the DC, and then you've got a ground wire and a couple of control wires, and there the 2 small ones are for they won't let you drive away if you're plugged in, and they'll communicate to the charger that somebody's plugged in and using electricity, and then that goes into the network and it broadcasts out that how many of these chargers are available if you're driving on by. And so that's what the 2 smaller ones are for. And this is the SAE J1772. Here's a few additional contacts in this one here. And this one is if you either have DC or AC, depending on where you plug in, it keeps it pretty flexible. So, where'd my cursor go? How long does it take to charge? Well, if we got 3 to 4 miles per kilowatt hour on level 1, 1,200 watts, Then every hour you put into 1.2 kilowatt hours. That's about 4.8 miles. So we're looking at somewhere in the 4 to 5 miles per hour rate of charging, depending on how you drive your car. So a rough estimate, hour of charge, 5 miles. Have a level 2 charger at 7,600 watts. That will increase the battery charge by 7.6 kilowatt hours per hour. Multiply that by 4, and you're up somewhere around 30 miles an hour for charging. Now that seems like you're driving pretty fast while you're charging, but we're just talking in a way of describing that every hour you can put 30 miles into your electric tank. So if you drive 30 miles a day, then 1 hour a day or 1 hour a night plugged into your garage gets you 30 miles for the next day. But if you're going to drive 60 miles, you got to stay plugged in for 2 hours. Wow. Well, some cars are plugged in for even more than that at night in the garage. So you can use your own imagination to figure out how many hours it would take to charge for the number of miles you're going to drive in a day. And because of that, lots of folks are going to be doing that. If you're out on the road driving a long distance, then in an hour you can add about 125 kilowatt hours, except the fact that generally they don't have a tank of or batteries that will hold 125. So the Cybertruck, I guess, has 135 kilowatt hours. But the other thing we have to remember is that as you're charging, just like with your phone or anything else, once you start to get close to 80% charge, it starts slowing down the rate of charge so the batteries cool down, because in order to know where we're at 100% charge, 100% charge is different depending on the temperature of the batteries. So a lot of variables in the miles per kilowatt hour equation. So these are rough estimates, but they're fairly conservative estimates, and they're a reasonable way to get started on what's going to work. What do you want in the charger? Well, the basic one is going to be compatible. It's going to talk, communicate. How long is it going to take? What's it going to cost to put it in? One nice thing about most of the cars come with the level 1 charger as part of the purchase price, and you can plug it into a 20 amp outlet in your garage. So there's a zero cost for charging in that case. Other cars, they sell them with 2 years of free electricity if you go to their charging station. The Kia people seem to be doing that these days, and the Tesla people have been doing that. But then you have to drive somewhere to get that free electricity. So maybe you just do it at night at home and be content. Here's your J1772 again, code compliant. And again, you see the power pins, the ground, and the communication pins. Advanced charger, bidirectional. We've got a whole new webinar, 2 hours on bidirectional charging, because it's really interesting what this could do in large quantities in terms of helping to stabilize the grid by charging when there's excess renewable electricity and then discharging back to the grid when the grid needs some electricity. It's interesting. In any case, they're adaptable, portable, smart. Smart meaning they communicate a lot of different ways back and forth. Maybe with the utility, about whether the utility wants to give you some electricity or whether it wants to sell you some. It's all been worked out. So what if we want to add a charger and we have an existing electrical service? What do we do? 220.83 has an existing single family. 220.84, you can do that using for a multifamily. And then you move into NEC 625.41. So that's where the rules are. and there are other sections for other kinds of places. But if we had a 1,500 square foot dwelling, we might have a load calculation look something like this. Air conditioner, 3-ton air conditioner would be about 3,600 volt amps. Washer, dryer, refrigerator, and appliance circuits probably all total out to about 16,000 volt amps. The electric water heater and the electric range. Why didn't I list these separately? Because my computer screen goes horizontally instead of vertically. That's why. In any case, following the rule for adding a load, take your first 8 kilovolt amperes at 100%, that's 8,000, the remainder at 40%, that's 13,040. Now, after you do that, then you say, okay, what kind of a dB? Well, there's other things you got to do. We got the your diversified load from this is 21,040. Okay, so you got 87.7 amps. Then you have to add stuff because notice the air conditioner is not on here and the heat isn't on there. So you have to add the air conditioner and you also then have to add the electric vehicle. So if we take 125% of a 9,600 watt or a 40 amp charger, that means you got a 50 amp circuit breaker, and we have to add then 50 amps to the previously calculated 87.7. So we add 50 to the 87.7 and we get 137.7. So that means we can put in a 40 amp charger as long as we consider it to be a 50 amp. And you simply go by the size of the circuit breaker in 150 amp service, in most cases without having to upgrade the service. Okay, let's say most cases, but you got to do the calculation because you don't want to be popping your main circuit breaker. Of course, there are one nice thing about these chargers is that most of them you can, there are settings that you can set to, even if it's capable of doing 40 amps, you can back it off to 32 if you need to, or 24 if necessary to get a 30 amp circuit breaker. Had to do that yesterday for a job. They can only add a 30 amp circuit breaker in order to stay at 150 amps. In any case, it's easy enough to do the calculation to figure out just how big of a level 2 charger you can install in a residential configuration. And in a lot of cases, 150 amp service is all you need. 220.87, you can do your average of your maximum peak demand over past 12 months. That's kind of hard to do in a residential where you don't have to pay for peak demand. But if you have a condominium where you're looking at the house load, where you have a general service demand rate, for example, then you're going to get billed and you have a demand charge for the highest 15 minutes of demand during the month. So if you have that, it's very straightforward to look at the last 12 months of demand by looking at the electric bill and see what the maximum demand was. We're going to take a look at one of those because it's kind of interesting. So in any case, you can, in fact, actually put instrumentation on and measure your consumption for a month, as long as you do it for the month that's expected to be the maximum consumption for the year. And then you just add 125% of that. And then you use that as your base. So anyway, and instead of the calculated load by NEC 220. But larger building typically has a general service demand rate, and so that's pretty straightforward for doing that. Then you add 125% of the new load, or you add the new load, which is 125% of the actual charging current, to 125% of the maximum monthly demand. And then you compare that with your calculation you had in 220.83. And if the 220.87 comes out lower than 220.83, you can use that. Okay, so a little more 620 points, NEC 625. I'm just going to click these out here because if you're really interested, you can just go to, you can either look at the slides again. 625.48 is particularly interesting because it says the National Electric Code is all ready for interactive systems where you can sell back to the utility because they already exist in stationary systems, battery backup systems in the house. IEEE 1547-2018 takes care of that, and it's all covered in UL 1741. Why does the charger have to be more than 18 inches above the floor? Very simple, because the outlets, electrical outlets in the garage have to be more than 18 inches above the floor. Why is that? Why, that's because if you park a gasoline vehicle in a garage, if there's any kind of a gasoline leak, my goodness, those gasoline vapors generally, hopefully, stay within 18 inches of the floor. So anything above that, if you unplug something and it sparks, it's not going to light the garage on fire. So all these dangerous electric vehicles, somebody was thinking about gasoline vehicles possibly posing a danger with gasoline leak way long time ago, because this has been in the National Electrical Code for a long time. And I've been reading a lot of National Electrical Code since 1975. So evolution of the charger. Here's the basic one-way charger. Looks like this. Plug it in, charge up the car. And there might be some limiting in the charger that says, oh, there's other chargers turned on right now, so we're going to let them have some of the electricity, and we're only going to take our fair share, and we're going to just play by the rules of whatever has been programmed in the system on how we're going to share this electricity. So there's some load management involved on a basic one-way charger, but it's a one-way. You charge it up. But what's coming up is the bidirectional. Whoops, and I clicked too hard. Let's see if we can go back to that. Let's see if we can find that again. There it is. So once again, you've got communication now dealing with what's going to the vehicle or what's coming from the vehicle. Okay. So pretty straightforward. Hurricane, you're not going to drive anywhere anyway because trees are all down across the street, so you might as well leave your electric vehicle plugged in and save that 75 kilowatt hours to help run your refrigerator. As long as you are able to recapture it, you're good to go. So let's look at energy efficiency as another thing that may affect the future electric. And what are some of the things we might do? Well, there's a lot of buildings out there, that's for sure, and almost every one can be made greener, including the one I live in. From my side, what I see is, for example, we have two 5-horsepower pumps up on the roof that are running simultaneously when it's designed for only one of them to work. And just shutting one of them off, there's 5 kW back, 5 kVAs back available for somebody else. One day, maybe they'll listen, maybe they'll do it. Used to do it, but y'all may have noticed that the experts all come from at least 100 miles away. You can't be an expert in your own building. I think you might call that Messenger's law. That's certainly what I've noticed. Nobody particularly wants to listen to me. Anyway, we'll leave that for another day. Fossil fuel heating, New York City, trying to get people to cook with electricity instead of with gas. If you have your renewable electricity equipment, well, that's pretty clean and maybe a little cheaper as well. After all, that's why the utilities are trying to install it, to produce more reliable, less expensive electricity. They can make more profit on that. Refrigeration, air conditioning, ventilation, they can all be made more efficient. Refrigeration has gone way up in SEER in the last 40 years. Lighting, convert to LEDs. My goodness, look at the lumens per watt on an LED compared to an incandescent light. So much more. That's why a lot of these buildings that are designed with 3 watts per square foot, that's based a lot on incandescent lighting. And so a lot of these buildings where your demand is calculated, you measure the demand and it's a whole lot less than the one that you would predict by doing the calculating the load. So better doors and windows. Florida, that's becoming pretty popular. Plug the air leaks, upgrade the insulation, make the landscaping more energy and water efficient. Or your watering system can be made a little smarter so that it knows what the soil is, what time of day it is, what the temperature is outside, whether the grass needs more or less water today than it did yesterday. And they're cost effective because they're selling them. And you don't sell things unless they seem to be able to prove that they're worth it. I saw a lot of these in Canada back in July. Lots of mini splits. These things are incredibly efficient. They can have an SEER of up to 42, and they operate down to minus 13 degrees Fahrenheit. And the Canadians have certainly picked up on this. And I wouldn't be surprised. I haven't driven them very much in northern United States, done some in Minnesota recently. But I'm guessing that these are going to pick up more in the United States as well. But SEER up to 42, the original energy efficiency for building construction codes were requiring a minimum SEER of 8. 5 times more efficient. That's amazing. Then there's the energy recovery ventilation. Countercurrent heat exchanger. You got ventilation requirements in a commercial building. Good idea to have ventilation in a residential building. Maybe you have a range hood, who knows. Point being, if you have countercurrent, then if you got hot air going out and cold air coming in, the hot air warms the cold air, so the cold air doesn't have to be heated as much because it gets heated by some of the air that's being exited. Or reverse the situation under the system of air conditioning. And energy recovery simply says that if you condense the water out of the hot air coming in, you're going to have a condensate drain. But that's even better to reduce some of the humidity. And they certainly talk about that story down here in Florida. And in the last couple of weeks, not this week, but 2 and 3 weeks ago, we had some heavy duty humidity issues in our building. Heat recovered ventilation if humidity control is unimportant. If you're in a relatively dry climate, then you don't need the condensate drain. Just do your countercurrent heat exchanger and you're good to go. Again, roughly 90% efficient. So instead of letting infiltration take care of your fresh air, if you use one of these, then you can capture the benefits of either let's say of the conditioned air inside, one way or another. Domestic water heating used to be either a gas water heater and then maybe an electric water heater. If you compare, and then solar water heaters came in, and boy, they were great. But now, if you compare the cost of a hybrid electric water heater with the cost of a solar water heater, it might be really close, and it's worth the effort of doing the math, especially if you are a part-time resident, because if you're away 3 months of the year, that extra hot water that you produce with solar, nobody can use it. Whereas if you're producing electricity with solar and then using it to heat water when you need to heat water, then it gets used. But the nice thing about heat pumps is you get this gain of something in the neighborhood of 3.5 kilowatt hours of heating for every kilowatt hour of electricity that you use. All right. And that depends on how the mode of use of, but people I know who have hybrid water heaters, they try to run them in the hybrid mode because that's where they save the most money. They do have an option of backup with straight electric if you need to heat it faster. So you still plug it into your 30 amp circuit, but you're only using a whole lot less than about 25% of that if you're using it in the hybrid mode. Okay, so it's possible, and it's worth doing the math to see whether a heat pump water heater, call it a hybrid water heater, is worth your while. And the other nice thing is a friend of mine in Florida here who has one, he loves the way it cools his garage because as it heats the water, it cools the garage. Doesn't work for me in a condominium, but and my concern of putting one into our little closet where our water heater is that cool air could cause condensation on the walls, and we could have a mildew problem. So we opted not to do that. But so not everybody necessarily can conveniently do this, but something worth considering. They look like this. That's the 50-gallon version, and that's pretty much what any family of four would want. And the marginal cost, if you do the math, generally worth the expenditure. Also considering they generally have a longer warranty. So, smart irrigation control, neat stuff. They can adapt to weather by adapting to grass, soil, shading, season, temperature, all kinds of stuff. And you can get by with maybe 80% less water. And if your water is pumped water from a water pump from a well, that's 80% electricity used for your water. And if you didn't pump it, somebody else did. And so you're saving 80% of their electricity and you're saving 80% on your water bill, at least that part which is used for watering your grass. So again, these are mostly cost effective. And one of the more popular ones like to kind of communicate by Wi-Fi. So you can just check on it any place you are, see what's happening with your grass. So, saves electricity for pumping. Let's take a look at zero energy buildings. By the way, I haven't paused at all. I don't know if anybody has any comments or questions. Let's take a look. I'm going to just pause and open my participant panel here. And if anybody has anything they wanted to, are we going too fast, too slow? Is there anything interesting here? Is it boring? Are you falling asleep? Just take a break here for a minute and let's find out anything that's okay. Are we okay here so far? Everybody can still hear? If you fell asleep, you fell asleep on something comfortable. Oh my gosh, nobody raised a hand. That's the test. Oh, John's awake. Okay, good. We're okay then, John? Pete, Brian, Don, Carl? All right, good. Yeah, don't hesitate. If you have a question you want to ask, oh, wait a minute. I see here something here. What's over here? Q&A. There are some Q&As. Oh, okay. Okay, good. Okay. Thank you, gentlemen. And we are 6 gentlemen. No, 3, 7. Okay. I don't like the mistake of implying all gentlemen if they're not all gentlemen in the group. Okay, let's look at zero energy buildings. I'm not sure how many people are familiar, but it's kind of a special area. And like I say, it's not a matter of just using zero energy, but it's a matter of zero source energy is what it's all about. This is a nice zero energy center out on Long Island in New York. And if you might, some of you may have been out there, it's a really nice place. It's kind of a museum-like. but it's designed as zero energy. You can see the photovoltaics up on the roof. And this is the energy storage element out, actually off to the left here, and as from the view of the building. So what about zero energy buildings? How do they work? Well, the zero energy, we have to talk about site boundaries. And so let's say we're going to rebuild this place with a zero energy building. We have a site boundary, and whatever is in that site is something that uses energy. And on that site is something that produces renewable energy. And off-site is something that delivers other energy, which might have a renewable component to this site. The other thing that's there is that the site exports energy. And usually it exports energy to the source of the delivered energy. And if, in fact, the energy exported to the delivery source is equal to the energy collected from the delivery source, then it's a zero energy deal, net. In other words, there will be times when energy is coming into the site, and there will be times when energy is going out to the site. So that over a year's time, the net energy used by that site from external sources is zero. And that's your definition of a zero energy unit. So let's design one just for the fun of it. We've got plenty of time here. We got almost 55 minutes. So, well, actually, there's a few other things we need to talk about, so we'll have to design it in less than 55 minutes. So first, we have to estimate the direct building energy use. This seems to be some kind of a flood here. They're not using any electricity right now, given the way the water level is on that service entrance. But assuming the water level goes down, we can pay some attention to how much energy the building would use. And but we have to talk in terms of source energy. So we need to be able to do source energy conversions. So how do you do that? Well, we have to have some, first let's get some basics down. Everybody knows that 1 BTU will raise the temperature of 1 pound of water by 1 degree Fahrenheit. And a kilowatt hour is 3,413 BTUs if we convert 100% of that kilowatt hour into BTUs, which is pretty much what happens in a water heater. That doesn't mean we get all 3413 at the faucet, because there are losses in the delivery system and in the tank itself. But the conversion itself is pretty fast, because the second law of thermodynamics doesn't apply to this particular system, except where the electricity maybe is generated. A therm is 100,000 BTUs. A barrel of oil is 42 gallons. And that barrel of oil is going to have 5,800,000 roughly BTUs. You get the really good stuff, you get 5,800,020 BTUs maybe. And a gallon of fuel oil, number one, is going to have roughly 137,400 BTUs. So that's your source energy that's available. That doesn't mean you can use it all, because if you're burning that oil in an automobile, you're not going to get all 5,800 BTUs out, or 55.8 million BTUs out of it. You get about 35% at most out of it. That turns into energy of motion, or maybe running your stereo or your air conditioner or something like that. So these are useful numbers to use in making conversions. And so let's list all the sources and let's see what we got. Going to rebuild here, try a zero energy unit. So let's build, say, a 1,500 square foot building, uses 75 kilowatts, in a year it's going to use 7,500 kilowatt hours of electricity. And we're going to assume there's still natural gas there, because then we can use the source energy conversion terms for both of these. They might decide to use an electric water heater, electric stove instead. You never know. Let's see. Okay, I think we have a question here. Let's take a look. Let's see if it's in the chat, or is it elsewhere. John, did you have a question? All right, let's see. Maybe that was a leftover hand from the question I had. Okay, I don't see any open questions right now, so maybe that was just a leftover. Okay. So what are the assumptions here? First, we have to convert our 7,500 kilowatt hours to BTUs, so that gives us 25 million or so of those. Then we convert our electric to source energy, because remember, the source energy conversion factor for electricity is 3.15. So that means we have 80,632,125 BTUs of source energy that it would take to make these 25,597, 500 BTUs of electricity. If we're using second law of thermodynamics type conversion factor, and that's what this 3.15 is based on. Natural gas into source energy, 500 therms. That's times 1.09. Now, why 1.09? Well, because natural gas is going to be used for direct heating, not for converting into something other form of energy. So therefore, if you're heating water with the natural gas, it's about 90% efficient. If you're cooking with natural gas, most of that heat is going to be used in the cooking. So the conversion factor is 1.09. That means you only need 54,500,000 BTUs of natural gas. Even if it's the furnace, you're directly using it for heating and converting it into BTUs, not into electricity. Okay, so we add those up, 135 million BTUs a year. So how much photovoltaics are we going to need if we want to make 135 million, 132,000, 125 BTUs? By the way, I rounded that off at the decimal point. So let's figure out how much PV we would need, just for the fun of it. After all, this work has to be fun. Otherwise, why bother do it? Okay. It turns out an unshaded south-facing array can be expected to produce about 1,500 kilowatt hours per kilowatt per year. Now, National Renewable Energy Laboratories has a very nice program that can be used to calculate exactly what you can expect per year based on typical meteorological year data. If you want to know and use a number different than 1,500, or if you maybe have a west-facing or north-facing, you can still make electricity. Not as much, that's all. So if we have a 1,500 kilowatt hour per kilowatt per year opportunity, what can we do with it? Well, first we convert to BTUs, that's 5,119,500 BTUs per year per kilowatt of photovoltaics. Now we convert it to source energy because we got 3.15 factor. After all, if we're going to make it by the sun, it's an electricity to electricity. The electrons are all the same color. So therefore, that converts to 16 million BTUs for that kilowatt of PV. How many now did we need? We needed 135 million BTUs. So if we get 16 million per kilowatt, that means we're going to need 8.38 kilowatts of BTU of PV. Now, is that, I think I said at the beginning of this webinar that last 2 days I've reviewed about 80 kilowatts of residential PV and averaging about 13 kilowatts per unit of residence. So this almost sounds like it might be doable. Let's find out what it takes to be able to do it. If you have an array with 20% efficiency, that's low for today's, you got up 21, 22%, but let's assume 20%, just in case it gets dirty or something like that. So or maybe after 2, 3, 4 years, it'll lose some of its efficiency. The intensity of the sun at peak intensity is 1,000 watts per square meter. So therefore, this module will produce 200 watts per square meter at standard test conditions. So 8,380 watts divided by 200 watts per square meter gives us 41.9 square meters, which is 451 square feet of south-facing roof space that we need. So what's that, 10 by 45? 20 by 22 and a half? That's doable, isn't it? So if you have a 400 watt module, you'd have 21 of them. You get that 8,380 watts. Then you have 20 watts to spare. So you check the dimensions, make sure it'll fit on the roof. And if it does, and if the price is right, 20 cents a module, whatever, you go for it. And of course, you have to decide on inverters and so forth. So what are the trade-offs? Well, maybe you can make the building appliances more efficient. We just got a new induction range. Boy, that thing's really dandy, and I'm pretty sure that's going to use a lot less electricity. Maybe not a whole lot less, but it's going to pretty clearly use less because the heat goes just into the food, not very much goes elsewhere. We could use less PV then. So in other words, if we reduce the electrical load, then you reduce the amount of PV you need in order to get your zero energy building. So it's a trade-off, and you see, well, that induction range wasn't cheap. Is it going to pay for itself? Or maybe it's just nice to have it. Who knows? In any case, the cost of the greater efficiency can be compared to the cost of more or less PV. Well, in my case, I can't put up any PV. So the only option I've got is try to be more efficient. Different orientations for PV array, of course, we talked about that. And you just have to increase the size and of course that increases the cost a little bit and cuts back a little on the payback time. But highly likely you'll still make your electricity for less than whatever the local utility rate might be. That's typically the cost of electricity for residential be in the neighborhood of, if you got to talk about the levelized cost of electricity, which means how much you have to charge for your electricity if you want to pay for the cost of your acquisition, installation, operation, and disposal. You have to charge somewhere in the neighborhood of 7 or 8 cents a kilowatt hour for your residential electricity if you wanted to break even over the life of the system. So gives you some idea of whether it's probably not a bad idea. And this is why it's happening. That's why it's going on. And whether we do it here in the United States or not, Chinese aren't going to wait for us. They understand the math. In India, they understand the math. The Europeans understand the math. So, economics are very good. So let's look at savings in energy costs versus additional mortgage payment for 6 U.S. cities if we build one of these zero energy buildings. And look what happens. Look at Atlanta. The extra mortgage costs $100 a month, but they save $152 on their electric bill. $52 a month tax-free. Go to San Francisco, 217 versus 91. Well, yeah, you've probably read about how expensive electricity is in California. It's a whole lot more expensive than other places. So most of these differences in cost are not necessarily, sometimes you got some differences in building costs as well. But notice the difference in the mortgage is pretty close, around $100 a month, except in Houston. But the savings, that is a significantly bigger difference, and that's due to electric rates in those areas. So almost looks like it's worth it, doesn't it? How about energy storage? How about that? Well, let's talk about it with some history. We've had small energy storages around a long time. Batteries in cars, flashlight batteries, all kinds of stuff like that. And historically, there have been a lot of the first photovoltaic systems generally had energy storage. They were standalone. They were not connected to the grid. And they had DC loads. And then there were DC coupled grid connected systems. What's the DC coupled grid connected system? Well, we're not going to go into a whole lot of detail on that, but a DC coupled grid connected system is simply the way energy storage is coupled in to the system. And in a DC coupled, the energy storage is done by a DC battery that charge with DC and discharge DC. An AC coupled grid connected system uses the inverter, comes ahead of the battery, and the advantage of the AC coupled system is that the energy from the AC generation goes directly to the load at the same time that it's supplied to the batteries. And if the batteries don't need it and the load uses it, the efficiency there is about 98%. So the AC couple tends to be a bit more efficient. In the past, they've been kind of expensive, but now they're not. They used to be kind of complicated. I was there. I know exactly how complicated they were in the year 2000 and year 1995. You had to program them on site to make sure you got it right. So generally what people ended up with was something that was utility, main disconnect, main distribution panel, and there's your electrical system, because things were kind of expensive back 40 years ago. But we talk about Mr. Musk, but he's not the only guy. But everybody hears about Tesla batteries and things, so we'll talk about Tesla batteries. And if you got a Tesla battery or an Enphase battery or any number of different kinds of batteries, you can do the following thing. You start with utility meter. You have a main disconnect with some feed-through lugs. Maybe in that main disconnect, you've got a distribution panel that has some interruptible loads. And then you have an automatic relay, and then you have a main distribution panel with a main circuit breaker, which has uninterruptible loads. And then we connect in a combiner panel, and then we connect in some solar with a PV inverter. So in other words, a combiner panel is an AC panel. And then we connect in some battery storage. And the battery storage, notice it's AC in, AC out, because inside that battery storage, there's a rectifier that converts DC to AC or AC to DC if we're charging the battery. And there's an inverter that converts the DC to AC when we feed back into the system. This particular system is a backup system, because that automatic relay, if the grid goes down, it disconnects the rest of the system from the grid, the power wall, or the inverter, senses that and says, hey, guess what? The grid is down. We have to do the job by ourselves now. So the inverter and the power wall, they get together, and the inverter stabilizes it becomes a voltage source instead of a current source. It stabilizes the system at 60 hertz. The solar makes the electricity. It goes to the loads if the loads want them. If the loads don't need it, then it charges the batteries. And if the batteries and the load don't need it, then it shuts down the array until something needs the electricity. So that's kind of a disadvantage. On the other hand, if the utility isn't there, and there's nowhere else for the electricity to go, that's the way the standalone, not the standalone, but the battery backup system works if it's just for battery backup. Now, the other way this thing could be used is that automatic relay wouldn't necessarily have to go in there. The utility could talk to that Powerwall or that inverter and say, hey guys, we need some electricity. If you have any extra electricity stored in your batteries, would you please, rather than charge the battery, send it to us? And the Powerwall says, well, we are at 90% charge already. We can send you some for a while as long as we can get some back later tonight. What's the deal? Well, we really need it now. It's 5 o'clock and we'd be willing to pay you 30 cents a kilowatt hour for it. Okay, man, you got a deal. And so for 2 hours, the Powerwall sends electricity to the grid. And then later on that night, the grid says, okay, now if you want to buy some electricity from us for 5 cents a kilowatt hour, we'd be happy to fill you back up again. The Powerwall says, well, yeah, as long as you're willing to deal with us tomorrow when the sun shines again. So interesting stuff going on with the system like this. And here's the more detail I just talked about. And so again, if you want the details, and if I talked a little too fast now to make sure we got done on time, the details are available. PDF of this presentation is available after the presentation. I don't know, maybe even it was even available beforehand. I'm not sure. So anyway, here's our energy storage at a small scale. It's pretty clear that at this scale, we can certainly scale this up and add whatever bells and whistles we want in terms of whether or not it disconnects from the grid if the grid has problems. Because the biggest problems the grid had are not by going down completely, it's by being overloaded. The last thing you want to do if the grid needs electricity is to shut off a source. So this is the time when the grid says, hey, I really am straining now and I could use your help. So you turn this around the other way around and you let the Powerwall at least power up the loads internally so that the dwelling or the building does not have to use power from the utility as much as it would have to do otherwise if the batteries weren't turned on. So it doesn't necessarily mean the battery power actually goes out to the utility, but the equivalent happens because the building itself uses whatever power it gets from the batteries and the PV combination rather than from the utility, which helps take the load off the utility and helps the utility to send electricity to others who need it, who can't provide their own needs. So interesting. And this is AC in, AC out. This is an AC coupled system. So how do you PV the size of PV in the storage? Well, a lot of people just say, well, I tell you what, I can afford 10 kilowatt hours of storage, give me that. And that's what you end up with. But there are more sophisticated ways you can do it. And this is just a way that you could figure out how much electricity you need if you needed it. I still got my camera on, don't I? I forgot to turn it off. I usually turn it off. You're not watching. You don't want to watch me anyway. If the maximum monthly kilowatt hour is 1,200 kilowatt hours, that's about 40 kilowatt hours a day. Okay. So how much uninterruptible load would you like to have? Well, you look at every load. If you leave out the hot water and the air conditioner and the dryer, because they would be the ones you would be least likely to want instead of your communications equipment and your some ability to cook with the microwave and some lighting and so forth. Um, maybe you'd like to have about 20 kilowatt hours a day. So that leaves 20 for all the other loads. So wouldn't it be nice to make 20 kilowatt hours a day with your solar? And we already know how to do that because we did that exercise just a little while back with our zero energy building. So 20 kilowatt hours a day is going to take about a 5 kW PV array. And that's not very much for residential now. So, and again, the NREL SAM program, by the way, if you're interested in this, just Google National Renewable Energy Labs or Google NREL SAM as it's abbreviated here, and it'll come right up. And you can download that for free for the cost of your email address so they can report how many people are actually using their work product. So gives you pretty reliable calculation on what you can do. So it'd be nice to store 20 kilowatt hours a day. So you select a storage unit with 20 kilowatt hours of storage. Whether it's one unit, whether it's 4 or 5 kilowatt hour units, whether it's some of them are come in at about 13 and a half. In any case, you look for 20 kilowatt hours of storage. And it'd either be 4 5s or 2 10s more than likely to get that exact 20. And that's about what people are ordering up these days. 20 is pretty average. Some I've seen 40, I've seen even 80. That's a pretty big dwelling unit that's going to take 80 kilowatt hours of storage. But in comparison, the electric vehicle storage tank is in the neighborhood of 75 kilowatt hours. And of course, they could use that once a day or even more than once a day if you fill it up more than once a day. What about the big systems? That's the small stuff. This is a big one. That's pumped hydro. Pump water uphill during the day when the sun is shining, or actually these were designed way, way, way back when they built the first nukes and they were making more electricity than the grid needed at night. And they were pumping water uphill at night to save it. Because once you got a nuke stabilized, you want to keep it there, running at that same rate. And you don't want to back off, so you want to use that electricity. So now these things are dually useful because they'll back up the nukes at night and it'll back up the PV at day. So you can be pumping water uphill all day long, except maybe during peak time, and then you let it run downhill and fill in the gaps. So pumped hydro. What's that one on top in the middle there? Anybody want to guess what that thing up there is in the middle of the screen? Go ahead if you want to guess. I bet somebody knows. Surely at least one person knows what it is you're looking at, that round thing, that cylindrical thing. Any mechanical engineers in the group? Well, okay, nobody wants to volunteer. Yeah, this is that's a spinning piece of big heavy steel. All right. That's mechanical storage. It's a rotating wheel. And it's really good if you get that up and especially if you have that drive an inverter, then the inverter doesn't much care what rate it's speeding or what the rotational speed is. And this so half I omega squared energy, you can store. This is a whole megawatt worth of energy you can store in their megawatt hour. So And this is really good for stabilizing utility frequency. Okay. Down below, you see battery storage. And lots of interesting stuff out there that's available for storage. This is another battery. This is your flow battery. And when you got flow batteries, you usually have a little bit of a raised walkway around them in case they leak. The flow batteries, their energy density is kind of low, but their overall cost effectiveness, there's a number of them out there. The most common, though, are the lithium variety, like number 342, 341, and so forth, at the very bottom in the middle. And that's your dry storage. So there's a couple of the storage. And here's a big example here. This is a Tesla system. Specifics on it was completed in 2017 over in South Australia. It happens to be capable of generating 100 megawatts of power. And by the way, battery storage has two metrics, the power and the energy, because not only the amount of energy stored is it important to know, but it's important to know is how fast can you drain it or how fast can you charge it. So the rate of discharge or the rate of charge is also important. And this can be discharged at the rate of 100 megawatts, and it will store 120 megawatt hours. And it took 140 milliseconds for this thing to crank out to deliver 100 megawatts when a coal plant went down back in 2017. Interesting. Very interesting. So 129 megawatt hour capacity. I don't know, what did I say? 120, 129 is what I meant to say if I didn't say the right number. So in other words, it'll deliver 100 megawatts for 1.29 hours, or 50 megawatts for twice that long, or something in between. So what do? As we can read about it, you charge it at night, you discharge it during the day when you need it, or if some other source goes down, then you bring this online. And the folks in South Australia seem to like this thing pretty well. Now this now is 100 megawatts and 129 megawatt hours. This is a small change now compared to some of the bigger energy storage things that are now going out in the field in the neighborhood of closer to 500 megawatts. So, and the cost is going down and the number of lifetime cycles is going up. And so therefore the cost per megawatt hour of storage is going down, and it continues to go down. Why? Because there is a market for it. There's a demand. So we get into this mass production operation. Pumping water uphill. Pretty straightforward picture of it here. No one will spend a lot of time on it, but pretty obvious what you're going to do. You're going to have to reverse the flow of the water. When you're pumping it up, fill it up in the reservoir, comes down, turns the generator becomes a motor to pump it uphill. And works fine. It really doesn't care what the source of the electricity is. You just tell it what you want it to do. Pumped hydro, it's going up. And in 2023, there's a pretty big jump. And who do you suppose was responsible for that? Anybody want to guess who in the world would have been installing pumped hydro in 2023? Anybody want to take a guess at that? What do you think, Pete? You want to do it in the chat, or you want to turn on your microphone? Either way works. Not the chat. I mean, in the Q&A. Maybe we got something. Just Q&A. China, Brian, and you. Okay, gentlemen, you're correct on that. I guess there's been a little publicity about some of the one of the pumped hydro plants that India is not too happy about China wanting to build because they're concerned about what if it breaks. They're going to get some pretty severe flooding. So there's a little pumped hydro is a little more complicated because it's a lot of land involved and a lot of environmental issues that could possibly be involved, but it's still happening. It's since 2010, we're 99.8 up to 139.9. And this is gigawatts. All right, this has nothing to do with gigawatt hours. It's the capability of pumped hydros to produce 139.9 instantaneous billions of watt. And so there's the pumped hydro storage. It's out there and it's still being built. And if you can do it in an environmentally friendly way, not that bad of an idea. And presumably the regulators and the demonstrators and everybody else involved will have something to say about that. Okay, what are some of the emerging storage technologies? Flywheels. All right, you saw the flywheel, the megawatt flywheel in that picture at the beginning. Get them up to 10,000 RPMs, that'd be pretty well balanced to do that, or they vibrate like crazy, but there's work been done on that. Capacitors, they're very good for transient voltage stability. Everybody who took electrical engineering circuits 1 learned that the voltage in the capacitor cannot change instantaneously. So therefore, capacitors are great for transient voltage stability. An inductor, meaning a superconducting magnet, since the current in an inductor cannot change instantaneously, a magnet is fantastic for helping to provide stability of transient currents, to reduce the possibility that they might exist. High power batteries, they're good for contingency reserves, loads following, additional reserves for forecast uncertainty, and so forth. And a lot of them are coming. I'm seeing a lot of those coming through now. A number of manufacturers coming out with some nice high power batteries that are being used in the residential market, and of course, they're also being used in the commercial market. Electric vehicles. If you can store 80 kilowatt hours in an electric vehicle and you've got 100 million of them on the road, that's a lot of stored electricity. And if it's plugged in and they can send it back someplace when it's needed, that's some pretty interesting opportunities. We got a whole 2-hour webinar on what the possibilities are for doing that. Hydrogen. There's issues with hydrogen, but they hang in there. The issue mostly is just low round trip efficiency. But they do have higher energy density than air. So hydrogen is hanging in there, and it's hard to know what we're going to see in the future. Weightlifting cranes. The only issue here is they started lifting concrete, but then they realized it took more energy and kilowatt hours to build the concrete than the concrete could return over the life of the concrete. And so they're using different materials now, more like rocks and things that don't have the same energy intensity as concrete. And the Europeans are doing these things, and you can look up lifting weight storage if you're more interested in this, and you'll see some big buildings that the Europeans have built where you simply have a crane that lifts weights when it has to store energy and the potential energy, and then you let it turn around just like instead of lifting water, you're lifting steel or rock or something else. Something that you can get more energy over the lifetime out of it than it took to build it in the first place. Data centers. Interesting. Between 2018 and 28, the United States data center electricity will increase from 9.9% to between 6.7 and 12%, supposedly. And that means it could go from 60 terawatt hours to 580 terawatt hours within the next 3 years. A lot of uncertainty in this prediction. And this big increase is happening between 2024 and 2028. This particular source, and by the way, 2024, about 25% of all electrical generation was from renewables. And the sources here are the yellow is a very nice report that the folks at University of California at Berkeley did, Berkeley Labs did for the United States Department of Energy. And I just read that. It's about 80 pages long. We don't have time to discuss the whole thing here in the next 15 minutes. But lots of good graphs and things. And it does show that there is an interesting challenge to meet the energy needs of data centers. The 24% US electricity figure comes once again for the US Energy Information Administration. So how do we make the terawatt hours? Can we do it renewably? Well, the fact that in 2024, the United States installed 30.816 gigawatts of PV and 3.128 gigawatts of wind and 0.293 gigawatts of other stuff. That's 1 year's worth. So these are gigawatts. Now we have to figure out how much storage can you get. So, well, you get about 1.7 terawatt hours per gigawatt of PV. That's, in other words, 1,700 kilowatt hours per kilowatt, because this is large scale. So these are all going to be optimally located in order to get the most economic benefit. And then about 2 kilowatt hours per terawatt hour for wind. Sorry, 2 kilowatt hours per gigawatt for wind. In other words, 2,000 kilowatt hours per kilowatt. And again, that's wind properly sited. So if we look at the amount of energy, annual energy generated by wind and solar in 2024, it's somewhere around 58.6 terawatt hours. How many do we need? Well, let's see. Can we do it? Well, if we continue this rate of growth, that would be 234 terawatt hours. Now, this is interesting. It depends whether you're in the United States or China or elsewhere. I can tell you that being in the PV business, we had 8 engineers in 2022 designing photovoltaic systems. We now have 2. So things are slowing down. But the opposite story is the case in China. If we're not buying their stuff, they're using it themselves and selling it to other people. So they didn't slow down. So in any case, we could do 234, and we could, if we set our minds to it, do a whole lot more than 234. If we increased our 20% annual increase in output, it would be more than that. So that's 234, and that compares with the 705. We could, 234 could get us up to 705 by 28. And so we could have 1,644 terawatt hours by 2028. New, generated between 2024 and 2028. So do we need the coal plants? Good question. There's even more esoteric questions involved. If you read some of the papers by, who's our friend who was into the AI business, which is the thing that really eats up the data center electricity, who says if we let them get as smart as people, then we're all dead, because people maybe aren't as smart as we think we are. So, there's a real possible Other comparisons that have been made on data centers are like, for example, I don't know how old you gentlemen are, but back again, there once was a whoops system up in Washington State where 5 nuclear plants were planned and they started building them. And while they were building them, they realized that they didn't need them, so they all went down the drain. So the planning, it's possible that something will happen that we won't need all this. And this is all going to happen within the next 3 years or so. So there's the estimate that was done by the Berkeley study has a very wide range, and this is the reason, because whether or not the need is going to be established, a fair amount of the data center energy uses for Bitcoin, for example. I don't know, I never bought anything with the Bitcoin. I'm not sure if any of you have. I'm not even exactly sure what it is, other than something that makes certain people very rich and other people very poor by bad investments. Anyway, just from an engineering standpoint, and that's what we're looking at here, but sometimes engineering decisions are influenced by other decisions as well. And we kind of have to keep an eye on that pulse of that as well. But it does look like renewables could supply the needs of the data centers even at their maximum requirements if we set our mind to it, and at an economically attractive price as well. So anyway, here's a couple of pretty good sources here if you want to take a look at the numbers that we've got. This is where the numbers came from. What about microgrids? Well, we talk about this is essentially the same story as the zero energy building, because this is a zero energy neighborhood. And it's basically the idea is to that point of common coupling there, that's the real red thing. That's the important thing that says, gee, if you can do it with a house or with a building where the building can still have enough storage to maintain its, or let's say internal and storage and generation capacity to make its own electricity, even if the grid goes down, and you do that on a larger scale, like on a neighborhood or like the whole branch of a distribution feeder, then you've got a thing like this. And a former graduate student at Florida Atlantic University, this drawing that she made for her PhD dissertation, and was on her committee, and she's kind enough to share the picture. So she did a lot of work on optimizing the performance of a microgrid, and it looks like they're doing this down in the Caribbean and other places, and probably will end up doing some of this in the United States as well. Whole idea is to optimally use locally distributed resources so that you have to depend on don't have to depend as much on the large transmission lines of distributed resources elsewhere. Taking care of the local loads, reducing the operating costs, minimizing emission levels, all good things, presumably. What does it do to the grid? Well, here's what we more or less have today. It's a one-way deal. You generate it, goes to the substation, goes from the substation out to a bunch of different places, different distribution lines. You have maybe a residential neighborhood or two, and then maybe you have a commercial neighborhood or industrial neighborhood where you got a lot bigger loads and bigger transformers. But that's kind of what today's grid is like. But what we are transitioning to, and highly likely will end up with, is something like this. A little more complicated. And you notice we start with a residential neighborhood. We got baby PV systems, 10,000 watts or something, relatively low loads, 100 amp, 150 amp loads, baby storage, 10, 15, 20 kilowatt hours, small PV systems. Some of these places maybe will have only PV, some will maybe have only storage, you never know. And then you go to the bigger neighborhoods where you have commercial and the bigger commercial systems and the hundreds of thousand of maybe a megawatt size, the bigger loads that have small photovoltaic systems, 100,000 watt size, and small storage, maybe in 100 kilowatt hour to 500 kilowatt hours, but still bigger than 20 kilowatt hours. Then you get to around the substations, and where there you got some really interesting stuff going on with even bigger storage, and except that we call it medium and medium renewable. And here we're looking in the 5 megawatt range for medium renewable power, and maybe 500 kilowatt hours of storage, 1,000 kilowatt hours storage. But then you get to the big storage and the big renewables and the utility scale stuff. And the main thing is, if you got a rotating generator, you don't want power going back to that rotating generator. They are not happy if you try to make them run backwards. So that bidirectional link is really important. That's the renewables and the storage, and all these all the way down the line, the communication and all. By the way, the protocols are all already established and already working and available for all of these communication links. So it's highly likely that by 2040 or so, we're going to see this in a pretty well defined form. And I may not, probably it's highly likely that I won't be here in 2040, but some of you might. And so you can check and see. Depend on you to keep track of this for me and report in wherever we might meet somewhere in the 2100 time frame. So this is not the end of the story. This is the beginning of the story because we're not really sure quite where it's going to go, but I've made an effort to predict what might happen. And welcome any comments now. We got a few minutes left. Let me take a look at chat, see what we got there. This is China. Let's see what we got here over in Q&A. Okay, now I'm going to go to participants and invite you to just chime in. We got a couple minutes. Let's have a conversation. This is a live webinar. Now it's your turn. What do you think about any of the topics here? You believe any of this is going to happen? Do you think it's all baloney? What are the likelihoods? Brian, you thinking about it? What do you think? No, somebody can turn on their mic sooner, or if you prefer typing something in, battery safety. Good point. Yeah, they've had some interesting issues with battery safety in California, haven't they? I'm betting on it. I'm betting on that. I mean, there's an awful lot of batteries out there all around the world, and you rarely hear about any issues. So it appears that they're on top of that. Well, Peter, I mean, I hope I'm right on this. Tried to make common sense arguments here. Tried to keep the politics out of it. Tried to base it mostly on economics and on people. Reading the chat box here. And we got my participant box open in case anybody wants to open their mic and have anything to say. Otherwise, it's almost dinner time for, well, maybe it's a couple hours off. I am kind of curious, though. I'm wondering where y'all are from, and if we could just do that, start and either type in where you're from and what is your background, what discipline and what area you're working in. It helps me in terms of preparation for these things to make sure that, so if we can do that in Q&A, I will light up my Q&A and, whoops, come on. Here we go. Let's see what we can get here. Oh, government subsidies, all of which are going away. You know, that is such an interesting subject. Nuclear power wouldn't be out there without government subsidies. They can't buy insurance on the regular market price. The government insures them. Oil depletion allowance. Every non-renewable source has subsidies, and they're now pulling all the subsidies out from under the renewables. And guess what happens? If you take a 30% subsidy out of something that has an LCOE, that's levelized cost of electricity, of 3 cents, utility electricity, it goes up by 30%. That's still a whole lot cheaper than most of the other sources that are, all of which are subsidized. So that's interesting, and we could spend a lot of time talking about that. I've got a lot of thoughts about that. And that's probably what's going to keep renewables alive more or less for a while here in the United States while we debate whether it's a good idea to have them or not. I kind of like rooftop solar because there's not much else you do with rooftops. It doesn't waste any land you might use for farming. And the part about the farming land being wasted, that's another story because they're noticing that solar farms, call them solar farm, with sheep. Sheep love to hide under solar panels to stay shaded. It's just that people aren't eating very much lamb these days lately. Is it viable without government involvement? If, as long as Wall Street is involved, Brian, I think we can still do it unless the government passes laws that says it's illegal. Brian, sounds like you're in Philadelphia suburbs. William from Cincinnati, Ohio, EMI, does that mean electromagnetic interference? Oh, okay, let's see. I gotta make my box bigger to see all, and Carl's from Brooklyn. Brian's consulting engineer, retired R&D electronics. Aha, okay. Great, great. I wonder what kind of electronics did you work on? Chips? Mechanical engineer, Wisconsin. Good place. This young man you're looking at in the upper right-hand corner of your screen, if I'm there, I came from Minnesota, moved to Florida in 1969. In any case, thank you all for being here this afternoon. I see it is 4 o'clock. We're right on time for stopping, and hope to see you again. Time to close it out. Whoops, Q&As. Okay, good. I'm gonna watch my participant box here, see if any other questions come in. And after the participants are gone, I think it's a good assumption there won't be more questions, at least not on the webinar. And once again, thanks for joining us.